So from this lecture onwards, let's explore about the Linux kernel modules and let's write a simple Hello World kernel module. First, let's learn how to write a simple Hello World kernel module. We'll learn how to compile the kernel module using the kernel build mechanism and transferring kernel module to the BeagleBone Black hardware, loading it and unloading it. Let's get started. First, let's start with understanding what exactly is Linux kernel module. Linux supports dynamic insertion and removal of code from the kernel while the system is up and running. The code what we add and remove at runtime is called a kernel module. Once the Linux kernel module is loaded into the Linux kernel, you can start using new features and functionalities exposed by the kernel module without even restarting the device. Linux kernel module dynamically extends the functionality of the kernel by introducing new features to the kernel such as security, device drivers, the file system drivers, system calls, and various other things. Basically, it's a kind of modular approach. You have a base kernel, and if you want to add new features, then you can add as a module to the running kernel. Support for Linux kernel module allows your embedded Linux systems to have only minimal base kernel image, and optional device drivers and other features are supplied on demand via module insertion. Example, when a hot pluggable new device such as USB is inserted, the device driver, which is Linux kernel module, gets loaded automatically to the kernel. That's why the code what we add and remove at runtime is called as a kernel module. Device driver is an example of Linux kernel module. So basically what I can say is a Linux kernel module is like a plugin to the running Linux kernel. There are two main types of LKMs, static and dynamic. Let's understand what exactly the static LKM. When you build a Linux kernel, you can make your module statically linked to the kernel image. That means module becomes part of the final Linux kernel image. This method increases the size of the final Linux kernel image. Since the module is built into the Linux kernel image, you can't unload the module. It occupies the memory permanently during the runtime. And the second one is dynamic Linux kernel module. When you build a Linux kernel, these modules are not built into the final kernel image, and rather they are compiled and linked separately to produce .ko files. We actually did this in the previous lecture. We executed a command modules. That command actually built the kernel modules, the dynamic kernel modules separately. That command actually produced lots of .ko files. You can dynamically load and unload these modules from the kernel using a user space program such as insmod or modprobe or rmmod. These are the commands which we will be using in future lectures to insert and remove the kernel modules, the dynamic kernel modules. So in summary, when you are building the kernel, you can either link modules directly into the kernel or build them as separate modules that can be loaded into the kernel at some other time. In this lecture, let's discuss about user space and kernel space briefly, because we use these terminologies in future lectures. So when an OS such as Linux is used, the code which runs on the CPU can be segregated as a user space code and kernel space code. When the kernel space code runs on the CPU, the operation mode of the CPU will be in privileged mode. That means the kernel level code can access many of the restricted resources of the system, such as memory, peripherals, processor instructions, control settings of the processor, etc. The user space program runs on the CPU. The mode of the CPU will be in non-privileged mode or in restricted mode. User space application cannot access those memory locations which it is not supposed to touch. So when I say user space, it just means that non-kernel codes. Example, any user level program. When I say kernel space, it just means that kernel level code such as Linux scheduler, the drivers, various codes related to different subsystems of the Linux, all are kernel space codes. If user space program wants any services to use the memories or the peripherals, so it can request to the kernel level code using system calls. System call handlers are actually kernel level codes which run in privileged mode to fulfill the user space request. That's the difference between user level code or user space code versus kernel space code. In this lecture, let's write our very first kernel module. Here is an example of a kernel module, a Hello World kernel module. It looks like a normal user space C program. But we have to understand a lot of things here. So because we write kernel module according to some rules, because the kernel module is going to run in the kernel space. Let's understand this program step by step. Here we can divide this program into a couple of sections. There is a header section, there is your code section, and there is a registration section, and there is a module description section. Basically, these sections are part of a kernel module. Let's go through these sections one by one. First of all, let's explore the header section. Here you have to mention the appropriate kernel headers for your kernel module. You can find all the kernel headers in kernel source tree in the path include Linux. That's a place where all the kernel headers are placed. In that location, you find a kernel header called module.h. Every kernel module should include this header file because it has got definition of various macros which you are going to use while writing a kernel module. Let's explore about what is the difference between kernel header versus user space header. For example, what you just saw here is a kernel header. So an example for a user level header may be stdio.h. That's a header file, what you find in the standard C library. That's a user level header. This is a kernel header. Since you write a kernel module that is going to be executed in kernel space, you should be using kernel headers. Never include any user space library headers like C standard library header files. No user space library is linked to the kernel module during a kernel build procedure. For example, you don't link your kernel module code with a C standard library. You don't do that. That's the reason you should not use any user space headers while writing the kernel module. Most of the relevant kernel headers are placed in the Linux source tree at the path include Linux. Let's move forward. Now let's explore about the code section. Here your code is nothing but collection of couple of functions. This is a normal C function, but it looks weird because it has got some kernel related syntaxes. That is very easy to understand. I will explain that. But it does look like a normal C function. Basically, while writing a kernel module, we use two entry points. Here, the first function is called as module initialization entry point, or in short, I call it as module initialization function. And the second function is called as module cleanup entry point, or in short, I call it as module cleanup function. Initialization function and a cleanup function. You don't see a main function here, so there is no main function. We talk about entry points. This function is an initialization entry point, and this is a cleanup entry point. Inside the function, you can write any code. For example, here I am using some kernel printing services or printing APIs to print some data. So we'll explore about kernel's printf later. Let's move forward. Let's understand more about module initialization function, why it is required. First of all, this is a prototype of a module initialization function. It should return int, and function name you can give anything you want, your custom name, and it will not be taking any parameters, so input parameters are void. The module initialization function must return a value, 0 for success. Non-zero means module initialization failed, so the module will not get loaded into the kernel. This is an entry point to your module, like main. We talk in terms of entry points. This function will get called during boot time in the case of static modules. In the case of dynamic modules, this function will get called during module insertion. That should be one module initialization entry point in the module. For example, if you compile this kernel module as a dynamic module, then this function will get called when you insert the module into the kernel using user-level programs such as insmod. Let's move forward. Let's explore more about module initialization function. What you do here, you do some initialization of devices, initialization of device private data structures. You request some memory dynamically for various kernel data structures and services. You request for allocation of major and minor numbers, the device file creation, various things you do in this function. So all these things we are going to understand when we write a character driver in the upcoming lectures. Basically, you do initialization related things in this function because it's an entry point. It's like a main. Let's understand the complete syntax of this function. You have got static keyword there, and you have got underscore init tag there. So what are those? We have to understand that. The module initialization function is module specific and should never be called from other modules of the kernel. Because it's the initialization function of a module, so why would other modules will call it? It is module specific. It should not provide any services or functionalities which may be requested by other modules. You should not give any services here which may be required from other modules. Hence, it makes sense to make this function private using static, though it is optional. Here, static keyword is actually optional, but as I said, this is module specific and it is private to module. Then it's good if you make this function a static function, right? Private to a file or private to a kernel module. That's the reason why we use static here, but it is optional. Let's move forward. I'll come to that init tag later. That is underscore init tag or a macro. So I'll come to that later. Let's understand module cleanup function. This is a prototype of module cleanup function. Return type is void. Function name can be anything. Your wish, you can give any name here. And it doesn't take any input parameters. This is also an entry point when module is removed. Since you cannot remove static modules, cleanup function will get called only in the case of dynamic modules when it is removed using user space commands such as rmmod. If you write a module and you are sure that it will always be statically linked with the kernel, then there is no need to implement this function. Even if your static module has a cleanup function, the kernel build system will remove it during the build process if there is an underscore exit marker or tag. What you do inside the cleanup function? Typically, you must do exact reverse operation what you had done in the module init function. Cleanup does undoing what init function has done. You free some memories which are requested in init function. You can also de-init some devices or leave the device in proper state. That's the job of cleanup function. Again, when we write some drivers, you will understand how to use this function. Basically, what you should remember here is for static modules, cleanup functions are not required if you are very much sure that it will always be linked statically to the Linux kernel. And if a module is dynamically loadable module, then a cleanup function gets called whenever the module is removed by using user level programs such as rmmod. In the next lecture, let's understand what exactly are these macros, that is __init and __exit. We'll understand whether it is really required or what's the advantage of having these macros or markers. I'll see you in the next lecture. In this lecture, let's explore about init and exit macros. These are called as function or variable section attributes. Basically, these are nothing but C macros, which are defined in include linux init.h. You can open the init.h file and you will find these macros. So you can see that here these are just C macros and which expand to something called compiler directive. These are compiler directives, or you can also call it as compiler attributes. For example, if you take the first case __init, which expands into __section .init.text. Here, this is called as a compiler directive, which directs the compiler to keep data or code in an output section called init. When you use this __init macro with any function, then that function code will be placed in a section called .init in the final kernel image. That's the meaning of that. Similarly, __exit is also another C macro which expands to this compiler directive, which directs the compiler to keep data or code in an output section called exit. Init and exit make sense only for static modules, remember that. I mean for built-in modules. __init is a macro which will be translated into compiler directive, which you just saw, which instructs the compiler to put the code in .init section of the final ELF of Linux kernel image. .init section will be freed from the memory by the kernel during boot time once all the initialization functions gets executed. Since the built-in driver cannot be unloaded, its init function will not be called again until the next reboot. That's why there is no need to keep references to its init function anymore. For example, this is the init function. If this module is a built-in module, then this function will be called only one time, that is during the boot time. And once this function finishes, then why would you need this function? Because it's a static function, no one is going to call it. Don't you think it's better to remove the memory occupied by this function code? The kernel can remove it, right, from the memory, which will save some memory because there are 100,000 built-in modules. Removing some memory for 100 modules would be huge, isn't it? The kernel is going to save a lot of runtime memory. That's why __init is a technique. By using that, we push that function into an init section, a separate section, which a kernel can free later. Let's continue with our discussion. So using __init macro is a technique. When used with a function, the kernel will free the core memory of that function after its execution. And also remember that it's an optional one. If you omit that, then no problem. You don't see any compilation warnings or errors. You can omit that. Similarly, you can use __init data with variables that will be dropped after the initialization. __init is for code or for function. __init data is for variables, init variables. What is the use of __ exit? You know that for built-in modules, cleanup function is not required. So when you use exit macro with a cleanup function, the kernel build system will exclude those functions during the build process itself. __ exit acts as a marker for the build system to drop the cleanup function in build process itself. It will not be part of the final kernel image. Let's say you have three static modules, module 1.c, module 2.c, and module 3.c. Let's say module 1.c's init function is m1 init function, module 2's init function is m2 init function, and module 3's init function is m3 init function. Out of these three init functions, m1 init function and m2 init functions are tagged with init macros. When you trigger the kernel build, all these three modules will be part of the final Linux kernel image. In the final Linux kernel image, a new section will be created that's called .init. And m1 init function and m2 init function will be part of that .init section. That means the codes of m1 init function and m2 init function will be placed in the section called .init by the compiler. When the kernel boots, the kernel calls m1 init function and m2 init function. And after that, kernel frees the memory which has been consumed by the .init section, because these functions will not get executed again during runtime of the kernel. That's the reason. What's the use of keeping that .init section? It will get freed. But in this case, m3 init function will not be a part of .init because it is not tagged with the macro __ init. So it will be a part of .text region. That's why m3 init function will permanently consume the memory during runtime of the kernel. And also remember that all __ exit marked functions will be dropped by the kernel build system, hence they will not be part of the final image. I hope now you get the idea why init and exit macros are used, and let me know if you have any questions. In the next lecture, I am going to cover module entry points registration. I'll see you in the next lecture. Now let's explore about the module entry points registration. So now you have got module initialization function and module cleanup function. You have to inform or you have to register your kernel module's entry points with the kernel. For that, we use some macros, which is given by the kernel. For that, we use module init and module exit macros. These are the macros used to register your module's init and cleanup function with the kernel. Here, module init and module exit is not a function, but a macro defined in Linux module.h. For example, module init will add its parameter to the init entry point database of the kernel, and module exit will add its parameter to exit entry point database of the kernel. Basically, you just have to give your entry point name as an argument to these macros. That's it. Now the next part is module description. These are some metadata which you are going to include in your kernel module. You can include module license, module author, and module description. For that, these macros can be used. Out of these macros, module license macro is very much important, where you have to mention license type of the kernel module what you are going to write. Module license is a macro used by the kernel module to announce its license type. If you load a module whose license parameter is non-GPL, then kernel triggers warning of being tainted. It's a way of kernel letting the users and developers know it's a non-free license-based module. The developer community may ignore the bug reports you submit after loading the proprietary licensed module. The declared module license is also used to decide whether a given module can have access to a small number of GPL-only symbols in the kernel. Go to linuxmodule.h to find out what are the allowed parameters which can be used with this macro to load the module without tainting the kernel. So with this macro, you have to use a string value. This string value indicates a license type. It could be GPL or non-GPL. And here you see the module license macro. And these are the options you can use with a module license macro. It could be GPL or GPL v2, GPL, BSD, MIT. All these string values you can use with that macro. If your module is proprietary, then you can use the string proprietary. That's why you have to use the appropriate value according to your license for which your module adheres to. When a non-GPL module is loaded, the kernel throws an error saying our proprietary module has been loaded, and the kernel will get tainted. There is nothing wrong in using proprietary as an option here. You can use that. That depends on you. And if you want to understand more about these licensing schemes, then you can read the kernel documentation, or you can just Google these license terms. You will get more info. In this course, for all our kernel modules, we will be using this option, that is GPL. Exit this. Let's move forward. And by using module author macro, you can mention the author of the kernel module. And by using module description macro, you can write a small descriptive message which explains your kernel module. After that, there is also one more macro called module info, from which you can create your own custom message. For example, if I want to include a message or a data such as a board is equal to BeagleBone, then I would use module info. Here, board is a key and BeagleBone is a value. When we do exercises, we are going to use all these macros. It will get clear when you see one example. So you can extract these module description details by running some ELF analyzing tools such as object dump or modinfo. There are various tools by which you can extract these metadata of the kernel module. So we'll see when we generate some driver object files. So we'll see all these things when we build our kernel module and generate a .ko file, that is kernel object file. In the next lecture, let's implement this Hello World kernel module, and after that we'll explore how to build a kernel module. I'll see you in the next lecture. In this lecture, let's implement Hello World kernel module and let's test it. Then we'll explore how to build it. Let's get back to our source, or not source, sorry. Just go to custom drivers folder and here create one folder. Let's start with Hello World 001 Hello World. Here just get inside this Hello World folder and here just create one file, main.c. Let's open main.c. You can use your favorite text editors. I'll be using Vim, or you can even use gedit or your favorite text editors. First, we have to include the header file. Let's do that. We have to include the kernel header file with respect to the Linux folder, Linux module.h. If you are not sure about that, let me save and exit this. Let's go to the source and Linux. Here there's a folder called include, and here there's a folder called Linux. Here you find most of the kernel headers. We are including a header file with respect to this folder, Linux, in the kernel source tree. After that, let's write our module initialization function and module cleanup function. Static int __ init, and let's give a name for our module initialization function. I would give hello world, any name you can give, hello world init. I would just give that, hello world init, and it doesn't take any argument, so void. That's it. Just close this. And now let's write module cleanup function. Static void exit hello world cleanup void, and give the function body. That's it. After that, register module init, give this name. That's it. After that, module exit. These are registration. And module license, just give GPL in capital letters. Module author, me. Module description, a simple hello world kernel module. And after that, you can give module info, some more info. I would want to mention what board I am using. I would just write board BeagleBone Black revision A5. Fair enough. This is a module initialization function which gets loaded whenever you load a kernel module into the kernel. Let's send some message to the world. For that, you can use printf statements, but you cannot use printf statements of the C standard library. So kernel has its own printf. We'll explore about kernel printfs later. Just use this function print info hello world. Actually, this is a macro which is a wrapper around kernel's printf, that what we call as printk. So it's a wrapper around that. We'll explore more on these kernel printing services later. This works exactly as printfs, what we have used in our user space programs. Just the name is different. Just give it as PR_info and PR info. This is hello world, sorry. Here you can write goodbye world. Remember that the module initialization function must return a value. If it is success, it must return 0. For that purpose, so I would use here 0. If it is non-zero, then module insertion will get failed. So module will not get loaded into the kernel. That's why for this example, let's use 0. For other examples, for real drivers, you will be returning some error codes or something like that. But here we are not dealing with any kernel APIs or something like that. We can just use return 0. It just prints and returns 0. That's it. I hope most of the things are implemented here. And in the next lecture, let's build this. But before that, we have to understand the build system. I will see you in the next lecture. In this lecture, let's learn how to build a kernel module. Kernel module can be built in two ways. One is statically linked against the kernel image, or it can be built as dynamically loadable kernel module. In most of the exercises in this course, we'll be writing and using dynamically loadable kernel modules. Let's say you want to build a kernel module as dynamically loadable kernel module. There are two types of dynamically loadable kernel modules. One is in-tree modules and another one is out-of-tree modules. What exactly is an in-tree module? In-tree modules means internal to the Linux kernel tree. For example, in the earlier videos, you actually ran a command modules, make modules, to build all dynamically loadable kernel modules of the Linux kernel. All those modules are called as in-tree modules. That means they are internal to the Linux kernel tree. There are another type of dynamically loadable kernel module that is out of tree, that is external to the Linux kernel tree. So the module what we just wrote, our hello world module, it is actually an out of tree module. Loading out of tree module taints the kernel. That is, kernel issues a warning saying out of tree module has been loaded. This is just a warning from the kernel, and we can safely ignore this warning. You will see that when you load that module to the kernel. Let me quickly cover about what are in-tree and out-of-tree modules. Basically, out-of-tree means outside of the Linux kernel source tree. The modules which are already part of the Linux kernel are called in-tree modules, that is approved by the kernel developers and maintainers. When you write a module separately, which is not approved and may be buggy, build and link it against the running kernel, then it's called as out-of-tree module. Hence, when you load an out-of-tree kernel module, kernel throws a warning message saying it got tainted. That is, a taint flag will be set in the kernel. Let's explore building a kernel module as out-of-tree. Later, we'll also explore in-tree building. Modules are built using kbuild, which is the build system used by the Linux kernel. It doesn't matter whether it is a static module or dynamic module. Modules are built using kbuild, that is kernel build. Modules must use kernel build system to stay compatible with changes in the build infrastructure and to pick up right flags to GCC. When you compile a user level program, what you do, you actually use a compiler called GCC, and you use various compiler flags, you use various linker flags to compile your program. So the same procedure we have to follow here, but while building a kernel module, you need not to worry about what kind of compiler switches or compiler arguments you have to use with the compiler. You just have to invoke the kernel build system, and the kernel build system will take care of using right compiler switches to the compiler. To build external modules, you must have a pre-built kernel source available that contains the configuration and header files used in the build. Basically, we have already installed the kernel source, isn't it? We will be building our module against that pre-built kernel source. This ensures that as the developer changes the kernel configuration, his custom driver is automatically rebuilt with the current kernel configuration. If you need more information about building a module using kbuild, you can go through the kernel documentation at this path. Let's move forward. There are some important notes I would like to mention. So please remember that when you are building a out-of-tree module, you need to have a complete and pre-compiled kernel source tree on your system. This we have already done. We have downloaded the kernel source tree and built it. The reason is modules are linked against object files found in the kernel source tree. You cannot compile your module against one Linux kernel version and load it into the system which is running kernel of different version. The module load may not be successful, and even if it is successful, you will encounter runtime issues with the symbols. That's why the thumb rule is have a precompiled Linux kernel source tree on your machine and build your module against that. There are two ways to obtain a pre-built kernel version. Download kernel from your distributor and build it by yourself. This is what we did. Or install the Linux headers of the target Linux kernel. Let's say you have an embedded system where the board is already running a Linux kernel of some different version. And now you have to write a driver for that board. What you do is you try to get the kernel source of that running Linux kernel version. So if you don't get full Linux source, then at least try to download the Linux headers of the target Linux kernel version and build your module against that. As I said, you cannot compile your module against one Linux kernel version and load it into the system which is running kernel of different version. Don't try to do that. That's the reason why we downloaded the Linux kernel source from the BeagleBone repository, compiled it and updated the Linux kernel image in the target. Now the version of the target Linux kernel and version of the source what we have got in our system is same. We are just going to build our module against the source what we have installed. Let's see the procedure to build a out of tree kernel module. And maybe in the next lecture, let's explore about building in tree kernel module. This is a command you have to use. Very simple command. You just have to use make command. That's it. Now the idea here is you have to trigger the top level make file of the Linux kernel source tree. That's the key thing here. And to trigger top level make file of the Linux kernel source tree, we use -c switch with a make. When you execute make -c, so make first enters into the Linux kernel source tree and it executes a top level make file. That's how kernel build system triggers. And when the make invokes top level make file, all the compiler switches, the dependency list, version string, everything will be utilized to build your kernel module. When make invokes the top level make file, you then have to direct the top level make file to your local make file or a local folder where you have kept your out of tree module source. And we direct the top level make file to our local folder by using the variable m. So m is equal to, you have to give path to your module source. And after that, this command also includes target options, and we'll explore about that in a moment. First, you have to use make -c path to the Linux kernel tree to invoke the top level make file of the kernel source tree. And when make invokes the top level make file of the Linux kernel tree, the kernel build system triggers, and you have to use the variable m to direct the build flow to enter into your local folder where you have kept your module source file. This is a command syntax. In short, make -c kernel directory and m is equal to path to the local module, and then you have to mention targets. So we'll explore about the targets a little later. Let's move forward. Now for the targets, you can use these options. If you want to build a module, then use a command modules. If you want to install the module, then use a command modules install. If you want to clean up all the generated files in the module directory, then use clean. And if you want to get any help, then you just use help command here. These are the different targets. We have already used these targets. We have used modules install. The same target option you can use with this command. Let's see creating a local makefile. As I said, the top level makefile will invoke the local makefile. This you need to create by yourself. In the local makefile, you should define a kbuild variable like below. You have to use a kbuild variable called obj hyphen. You can use 3 different values here, n, y, or m. And after that, you have to mention the module name .o. Let's understand how to create a local makefile. In the local makefile, you should define a kbuild variable like below. You have to use the kbuild variable obj hyphen, and you have to use the appropriate option. And then equate that to your module name .o. Here, x takes one of the below values. It could be n, or it could be y, or it could be m. If it is n, that means do not compile the module. When your kbuild system visits the local folder, it reads the local makefile and it reads this variable obj hyphen. It could be n, y, or m. If it is y, that means compile the module and link with kernel image. That means it's a static module if it is y. If x is m, then compile as dynamically loadable kernel module. All you need to do is you have to create a makefile and write this statement. Let's say I have a kernel module source file main.c and I want to build it as a dynamically loadable kernel module. Then I would just mention obj hyphen m is equal to main.o. When the kernel build system sees this statement, the kbuild system will build main.o, that is object file, from main.c, and after linking it will result in the kernel module main.ko. Remember that you should not mention main.c here. Main.c is a source. Our target is main.o, object file. That's why you have to write main.o. So the kernel build system creates the target, that is main.o, and after linking, the kernel module main.ko will be generated. I hope you get the idea, and let's try all these things practically on our Hello World kernel module, and I'll see you in the next lecture. In the previous lecture, we explored about the build command, isn't it? Now in this lecture, let's build our Hello World kernel module. Go to custom drivers folder, and we have already created one folder here. Let's get into the Hello World project. Here we have main.c, and let's create a makefile. Just run the command touch makefile and open the makefile. Add the obj variable, that's a kernel build variable, obj hyphen m is equal to main.o. That's the only entry you need to add for a time being. Later we will understand more complex syntaxes. That's it. You are initializing this variable to main.o. After that, let's save and exit. Now we are ready to build. You can build a kernel module for your host or for your target. Here main.c is a kernel module I can build and run on my host machine, or I can build for my target machine. First, let's try building the kernel module against our host machine, that is our Ubuntu machine. For that, you need pre-built kernel source of Linux kernel version which is running on your host system. First of all, what's the version of Linux kernel which is running on our host? To check that, just run uname -r. it is 5.3.0. And you can get the pre-built kernel source and the kernel header at this path: lib modules. You just mention the kernel version, that is 5.3. Here it is. Here, this is a pre-built kernel source and kernel header directory. You have to build your module against this directory if you want to build a kernel module against your host machine. Let's try that. So make -c. Now you have to mention the path to the Linux kernel source or to the Linux kernel header. Let's mention lib modules 5.3 5.3.040 generic. So generic, and then you have to mention build, and after that we have to define the m variable. M is equal to, it should point to the path of the current working directory. This is the current working directory. We can get the current working directory's path by using the environment variable pwd. So you have to get the value of the environment variable pwd. That's why we have to use $pwd. And after that you have to mention the command or target. So we want to build a module. You have to mention modules. There are different types of commands or targets: modules install, clean, and help. Remember that. In this case we are building, so we have to use modules here. I hope it is clear. First, what happens is, here when make is executed, it first goes into this path. It triggers the top level makefile, which it is going to find here, and the top level makefile get the value of m. M points to the current directory. The top level makefile visits your current directory and it sees a makefile there because you have kept a local makefile, and it reads the local makefile where you have written a obj-m is equal to main.o. It reads that, so it builds your main.c to produce the kernel object file main.ko. Let's hit enter. Here it is. Here you can see that entering directory. It went to that path, and after that it came to your local directory and it built main.o because that was a target mentioned in the local makefile, and it finally generated main.ko. So just do ls. If you change the target modules to clean, it will clean your working directory. You can see that everything will get deleted. Let's run that command once again. Now we got main.ko here. This is a kernel module. Let's insert that kernel module into the running kernel of the host. For that, you can use the user level program sudo insmod main.ko. Hit enter, and if you want to see the result, just type dmessage. So here you can see that we got these messages. You see there are two warning messages. The first one is loading out of tree module taints the kernel. That's a warning added by the kernel because you just loaded the out of tree kernel module. So you don't see this warning message if the module is in tree module. Let's try building and loading an in tree module later. After that, you see one more warning message here: module verification failed, required key is missing. So this is because the vendor, in this case Ubuntu, has turned on module signature verification. The kernel, which is configured by Ubuntu, compares the signature of the vendor on the kernel module. Since our kernel module is not signed off by the vendor, the verification fails. After that, the third message, that is hello world, is from our kernel module's init function. So when you loaded the module using insmod, the module's entry point ran and it printed this message. Now you can remove the module using the command rmmod. Now you see that the cleanup function of our module has executed and it printed this message. In the next lecture, let's build the kernel module for our target, and then we can transfer and test it on the target. Hey, welcome back to the lecture. In the previous lecture, we built our kernel module against our host, isn't it? And in this lecture, let's try to build our kernel module against our target. After that, we can transfer the kernel object file, that is .ko file, from host to target, and then we'll test on the target. Now you can use the same command here, but you have to do a couple of changes here. First of all, this -c should point to target's kernel source tree. Where it is? It is there in our workspace. Let's give that path. Workspace, LDD, source, Linux, BBB 4.14. Or you can also give the modules install path, that is root lib modules 4.14.108. You can also give that. Or you can directly give the Linux source path. And m is equal to pwd, that will remain same, and target, that is modules, will remain same, no problem. But you need to cross compile because you are testing this kernel module on the target, that is BeagleBone. So you have to cross compile. That's why we have to mention the cross compiler. Before this -c, mention arch is equal to arm and cross compile. That's it. Cross compile arm linux gnu eabi hf hyphen. This looks like a long command, isn't it? Later we'll learn how to include this command in the makefile itself. We need not to type all these commands. Everything we can derive from the makefile. So we'll learn that later. This is a command, and let's hit enter. There is an issue. This issue is because we used sudo. That actually messed up with the path environment variable. Let's fix this. What you do is just cat your bash rc, copy this path, toolchain path, just copy this. After that, just open sudo vi etc sudo's file. Just open this file, and here you see secure path. Here paste it. What you do is go at the end, give colon, and paste that path. That's it. And save and exit. After that, try again this command, sudo make. You can see that the module is built. If you just run file main.ko, now you can see that this is built for ARM. You can also run modinfo command on main.ko to extract the module description which you have given in the kernel module source. This is a string we added. Board is equal to BeagleBone Black. This is the description, this is the author, this is the license, and various other things. You can also run this command, arm linux gnu eavi hf object dump -h main.ko. You can run this command to analyze various sections of the kernel object file. Just hit enter, and you see here there is an init section. So your module's initialization function is actually placed in this section, .init.text. It is not placed in .text. And your module's cleanup function is actually placed in this section, .exit.text. And you see various other sections here, like this is the data section. Basically, it is showing 0 because our kernel module doesn't contain any data. Let's transfer this .ko file to the BeagleBone. I'm going to open new terminal and I'm going to connect my BeagleBone Black hardware to the PC. I'm going to power my BeagleBone Black hardware. Let me just open Minicom. You can see that the kernel is booting. Let's make one directory here. Let me call it as drivers. Let's copy our kernel module into this directory. Let's go to the host, and let's do secure copy, scp main.ko, and we are transferring this to target. Target's username Debian, IP address 192.168.7.2, and the path is home, Debian, drivers. This is a new folder we created in the home directory of the BeagleBone. Let's hit enter. Here there is some problem with the SSH connection. It is showing you the solution. You have to run this command. Let's run this command. If you are seeing this error, then only you need to do this. Otherwise, no problem. Let's paste this. That's fine. Let's try once again. So are you sure you want to continue connecting? Yes. It is asking you the password of the BeagleBone temp pwd, and you see here we copied main.ko. Let's go to the BeagleBone command prompt here and go to drivers. Here it is, main.ko. Let's do sudo insmod main.ko. So now here you can see that it has printed hello world. Actually, it got printed directly onto the terminal. So I'll explain why that happened in the later lectures when we discuss about kernel locks and kernel lock priorities. You can also run dmessage here to see that message, or you can just type dmessage bar tail. You can see that message. Let's remove that module, sudo rmmod main.ko. You can see that it prints goodbye world. Now we tested our kernel module on the target. In the next lecture, we'll build the same kernel module, but not as out of tree, but let's try with in tree building. I'll see you in the next lecture. But before that, try to do this and let me know if you face any issues. So in the previous lecture, we built our kernel module and tested on the target. We used this long command in order to build our module. Instead of running this long command, what we can do is we can include this in a local makefile and we can automate the build instead of typing all these things. That would be better. That's why we are going to edit our makefile now to include this command. First, what you do is you copy this command. Don't copy sudo, just copy this command. Just run the clean command. Your working directory should have only main.c and makefile. After that, let's edit the makefile now. I would use gedit makefile. It has got only one entry now. Let's add a couple of more entries here. Let's create a target. I would give a target name as all colon. This is a target. After that, hit enter. When you press enter, the cursor comes over here, isn't it? Give a tab. Press tab one time. Here you have to write the receipt. The receipt is nothing but our command. Paste the command, what you copied that. This looks very long. Let's shorten this. Let's create a couple of variables. I would create some variables. Arch is equal to arm. Cross compile is equal to, I would store this value into the cross compile variable. And let me create one more variable, kern directory is equal to, I would copy this as the value for kern directory. Let's copy this. After that, let's fix this now. Arch is equal to, instead of arm, what you can do is you can use this variable name. So $arch. This gives me the value of this variable. This will be replaced by arm. Here, instead of this, you can use this. Let me remove this. $of this variable. And instead of this Linux kernel source path, I can remove this. And instead of that, $kern directory. That's it. M is equal to, you have to give the pwd in parenthesis. M is equal to $pwd, which gives me the path of the current working directory. And this is a target or command modules. After that, let's create one more target for cleaning. Clean, enter, tab. So you can copy the same command and paste here. And instead of modules, give clean. You can also create one more command, help. You can copy this, paste here, and give help. These are the different targets. That's it. For the time being, let's use only this much and let's test this. Let me save this. There seems to be some problem here. Now let's save this and exit. Let's just run make. Here it is. You got the result. Main.ko is formed. If you want to clean it, make clean. So all files got deleted. And you can run make help in order to get the help menu of kernel build system. Let's again edit our make file to add one more target to build against our host instead of target. These are all building against our target. All these commands are using cross compiler. How about adding one more command to build against our host machine? You can add here one more target, host. You can use the same command, but you have to edit this. So you can use this command and remove this arch is equal to arm, cross compilation, everything. Kern directory, here let's use the word host kern directory. And let me do modules. Something like that. That's fine. And now let's define this variable is equal to lib modules. You have to use the name. So here you have to mention the kernel version of your running Linux kernel of your host. You can manually type it, or you can use uname -r. Just do $sign of shell uname -r and /build. You can also do something like this, or you can run uname -r on your command prompt, get the version string and paste here. Let's save this and Let's exit. Let's make clean first. Let's make host. You can see that now the kernel module has built for the host. You can insert that. It works. And if you want to build for target, then you just have to run the command make. This actually built the kernel module for the target. If I run file main.ko, it shows that it is for ARM. Whereas if I run make host, it shows different. For example, let's again run file main.ko. You can see that it is for x86. That's about creating a small makefile to automate our kernel building procedures. In the next lecture, let's explore about in-tree building. In this lecture, let's understand in-tree building. We are going to build our kernel module by adding our kernel module inside the Linux kernel source tree. You have to add the Linux kernel module inside the Linux kernel source tree and let the Linux build system build that. If you want to list your kernel module selection in kernel menu config, then you have to create and use a kconfig file. When you do menu config, Linux configuration will come in the form of menus, and from there you can select or deselect your kernel modules. You can add a small menu for your kernel module, and that's what we are going to learn in this lecture. Let's move forward. Now I have given a couple of steps here to add in-tree module to kernel menu configuration. First, what you have to do is you have to create a folder in Linux kernel source tree, maybe under the directory drivers char. Under this path, create a directory called my custom device or something like that. Any name you can give. I would give my_c_dev. And there you keep your main.c. After that, create a local kconfig file and add the below entries. This is a menu entry to select your module when you run a menu config command. A menu entry should start with a keyword menu and it should end with a keyword end menu. Inside the menu, you can add a couple of config items. One config item for each kernel module. You can give a small description which describes your menu. Like here I have used my custom modules. There could be many custom modules. We have got one which prints hello world. That's why this is a config entry or config item for my hello world kernel module. A config entry should start with the keyword config. All these are kernel documented kconfig writing syntax. You have to refer to the kernel documentation, that is this file kconfig language.txt, to understand how to write a better kernel menu configuration. In this config item, you have to use a config keyword along with an identifier. This is an identifier string. The kernel identifies your kernel module by using this identifier. It is usually written in capital letters. After that, your kernel module can be deselected or it could be selected. And if it is selected, it could be a static module or dynamic module. That means each kernel module actually has three states, that is Y, M, or N. That you can give by using the keyword tristate. You can give a small description about your custom module, as I have mentioned here, hello world module support or something like that. What is the default option? Whether it could be Y, N, or M. That you can give by using the default keyword. Default is M or default is N, something like that. That means by default, this module will be selected as dynamically loadable module. This identifier will appear in .config file when you do the menu configuration. So I'll show you that. And after that, you have to add the local kconfig entry to upper level kconfig. Let's finish the steps 1, 2, and 3, and later we can continue with others. Kernel source tree, source Linux. Let's get inside drivers char. Here, let's create one folder, mycdev. And after that, let's get into that folder. Here, create kconfig. Also, you should copy the main.c here. We'll go to the custom drivers, 001 hello world, main.c here. Let's open kconfig. Here, add menu. I would add descriptive name for my menu, my custom, or let me add fastbit custom module, something like that. After that, end this with end menu. And after that, let's add the first entry, config entry, config. You have to give an identifier name for your config entry. We are adding hello world kernel module, right? I would call it as custom hello world. After that, enter and give tab. Mention tri-state keyword. Just give a descriptive name for this custom hello world module. Hello world module support, something like that. And after that, mention the default selection for this kernel module, M or Y or N. Let me mention N. It is deselected by default. That's a small menu entry for our custom module. Let's save this and close this. Now you have to add the local kconfig entry to the upper level kconfig. That's how the kernel build system will detect your local kconfig. You have to inform that to the upper level kconfig. Let's do that. So let's do ls here. There is a kconfig, no problem. Let's go to the upper level directory, do cd, and this is the upper level directory. And here, open kconfig. Here, go at the end and add like this, source drivers char your folder kconfig. Let's add source drivers char mycdev kconfig. Fair enough. Save and exit. After that, next step is create a local makefile. So now let's get into our folder mycdev. Here, let's create local makefile. The next step is add this obj variable entry into the local makefile. First, let's go back to our command prompt and let's open the makefile what we created. Here, you should do obj hyphen, but you don't know whether it is M or Y or N. You don't know that because that what you are going to select using the kernel menu configuration. That's why you have to mention the config identifier what you have given in the kconfig. This is how you should write $, open the parenthesis, inside the parenthesis give the config identifier for your custom module, that is hello world. We have given the name custom hello world. This identifier has to be preceded with a keyword config. underscore. If the identifier name is custom hello world, you should mention it as config underscore custom hello world. Now this identifier later will be replaced by the menu configuration selection. It will be replaced by either N or Y or M as you select in the kernel menu configuration. After that, you have to give the target. You can use is equal to or plus is equal to, and here you have to mention module name .o. Module name is main.o. You have to mention the object file. Let's save this and exit. And what's the next step? So now the final step is add the local level makefile to higher level makefile. We have to establish the link. Let's go back to the command prompt. Go to the upper level and open the makefile. And you have to go at the end. Here you have to add your entry. This is in char, isn't it? In char you have created your own directory, that is my_c_dev. So you have to add that the way they have added here. I would add obj y because that folder is always selected. That's why I would use obj-y. To select that folder, we don't have any config item. Remember that. To select a kernel module under that menu, we have config item. But to select our folder, we don't have any config item. That's why I'm directly using obj-y. Plus is equal to your folder. my_c_dev.
人生如戏，都是喷嚏。让过敏下戏交给飞利浦，有效滤除99.99%过敏源，净化效率提升70%，360度净化大空间。飞利浦在，过敏不在。
That it finds another local makefile and it will use that kbuild variable obj- whatever the config item we have given. Let's save and exit.
Hôm nay thì bên máy tự động xin giới thiệu với quý khách một mẫu máy quét mới, tích hợp đầy đủ các chức năng. Chức năng quấn biến áp và chức năng quấn dây cho động cơ. Thì đối với chức năng quấn biến áp thì có thể quấn được các loại dây từ 0.1 đến 2.0.
Go to device drivers.
Sử dụng bàn phím để cài đặt. Máy có thể đảo chiều động cơ và dừng tại mỗi vị trí khi gặp công tắc hành trình để sử dụng trong trường hợp lọt giấy cho mỗi lớp.
Here you see our menu entry.
Reset lại thông số đã sử dụng và reset lại thông số mặc định của máy. Máy có thể lưu giá trị khi mất điện và lưu giá trị đã.
And you can see that by default it is not selected. If you go to the help, it will show you what is the symbol or identifier of that module. By default it is equal to N. Exit. And you can use the space key of your computer to select between multiple options here. It could be M or star. Star means this will be statically linked to the kernel. If it is M means it will be built as a dynamic loadable module. I would select M here and after that exit. So do you wish to save your new configuration? You have to press yes here and now open the .config file which is created. Just search for your hello world. Here it is. Let's quit this. Don't edit .config. Let's invoke the module building command once again. Make arch is equal to arm cross compile is equal to arm linux gnu eabihf modules. This is a command we use to build the loadable modules -j4. Here you can see that the module what we added is built. So you can see that the .ko file is generated. Let's get into that location, drivers, char, mycdev, and here just run mod info on that kernel module, and here you can see that it shows now entry is y. That means this module is now an entry module. When you load this module into the kernel won't throw that warning message saying out of tree module taints the kernel. That's about entry building of kernel modules, and with that note I would like to end this lecture, and let me know if you face any issues. Try to reproduce this at your desk. I'll see you in the next lecture. In this lecture, we are going to explore about debugging with printk. Printf is one of the best debugging tools what we have in user-level applications. When we write user-level applications, we heavily use printf statement. Printf is a C standard library API. When you work in kernel space, you will not have any access to the C standard library to access functions like printf or scanf. But don't worry, kernel has its own printf like kernel API called printk, where k signifies kernel space printing. This is very much similar to printf. For example, let's say if you want to print something in your user level application, you would use printf, something like this. Usage of printk is also same. Just replace your printf with printk, that's it. And if you want to print any variable value, then you would use %d or %x, something like that. Same thing you can also do in printk. So if you have used printf, then I don't think you will face an issue in using printk. Both are similar. When using printk, the message will go into the kernel's ring buffer. Simply we call kernel log, and we can print and control the kernel's ring buffer using the command dmessage. Suppose if you want to check the latest 5 kernel messages, just run dmessage pipe tail -5. If you want to check the first 20 kernel messages, then just run dmessage pipe head -20. Dmessage is a command in order to print and control the kernel's ring buffer. Please note that the printk does not support floating point formats such as %e or %f. There is a documentation in Linux source tree. The document name is printk-formats.txt. You should refer to this in order to understand what are the format specifier you can use with kernel's data structure. Suppose if you are using unsigned char or char, then you can use %u or %x. And there are some kernel specific type defs such as size_t, signed size_t. Whenever you deal with these type defs, then you may not be knowing which format specifier to use. For example, here size_t is a type def version of 32-bit value. Whenever you want to use such data types in your kernel module, then if you want to understand what exactly the format specifier for that, you have to refer to this documentation. Suppose if you are using a variable of data type long, then you have to use %lld. Just refer to this document if you need more information. This is where printk differs from printf. Printk comes with kernel log levels. Based on the kernel log level, you can control the priority of your printk messages. I mean, for your printk messages, you can assign priorities. or what we call as log levels. There are 8 such log levels. So a lower number indicates a higher log level or higher priority. And if you ask me what's the default, so the default print K log level or priority is 4. That translates into kern warning. All these log levels are C macros, which you can find in this header file, kern levels.h. What's the use of log level? The log level will be used by the kernel to understand the priority of the message. Based on the priority, kernel decides whether the message should be presented to the user immediately by printing directly onto the console. So when we loaded our Hello World kernel module, you saw the message directly got printed on the command line. That has got something to do with this kernel log. We'll experiment more with this in later lectures. Let's move forward. All kernel messages will have their own log level, so you may have to specify the log level while using print K. For example, take a look into this print K statement. Here, there is no log level visible, right? But the kernel will add the default log level set by the kernel config item config message log level default, whose value is 4. So the above statement is equivalent to print K, kern warning, and the message. The kern warning is a log level. It's a C macro actually. And after that, you have to write your message, printf like message. So note that there is no comma between log level and message. If you don't mention the log level, then it defaults to config message log level default config item of the kernel. Make arch is equal to arm menu config. And here go to kernel hacking. Here go to print K and dmessage options. And here you see default message log level. From here you can configure the default message log level. And it is by default set to 4. So you can change it while building the kernel. If you just check the help option here, you can see that the config item name is config message log level default. So default log level for print K statements with no specified priority. Let's exit this. So now let's understand what's the significance of kernel log level. Let's say you have two print K statements. First one uses kernel log level kern alert, and the next statement uses the kernel log level kern info. What's the difference between these two? Here what happens is the kernel message log level will be compared with current console log level. Remember that these are print K kernel log level. Apart from that, there is one more log level, what we call as current console log level. So there are two different types of log levels. The kernel or print K message log level will be compared with current console log level. If the kernel message log level is lower than the current console log level, then the message will be directly printed on the current console. By default, console log level will have the value of config console log level default. Its default value is set to 7. You can change it via kernel menu configuration or running the below commands. To know the current log level status, just run cat proxys kernel print K. At runtime, you can change the log level values using the below command. So by using the echo command, you can change the current log level values. Now again, let's check our kernel menu configuration. Go to kernel hacking and the same option, printk and dmessage option. Here you see one more log level, that is default console log level. So its value is set to 7 by default. The config item name is config console log level default. Default log level to determine what will be printed on the console. So your print case log level will be compared with this value, and if print case log level value is lesser than this value, then the message will be directly printed on the console. Let's run few commands to understand that. In order to read the current log level status, you can run the command cat proc sys kernel printk. Here in this output, this is default log level of the console, remember that. This is default printk log level or default kernel message log level. When I load this module main.ko, let's load that module. Now you see here the message hello world is directly printed on the console. That happened because we have used kern info to print this message hello world. We actually used pr_info. That actually resolves into printk kern info. So the kern info macro value is 6. 6 is less than 7. That's why the message is promoted to the console. Now you can change the default console log level. Let's make it 6. Let's see what happens. First, let me remove that module, sudo rmmod main.ko. And now let's use echo 6 and send it to this file. Hit enter. So it needs sudo permission. Let's give sudo. So it doesn't take that. No problem. Let's do sudo -s and let's try that again. Let's do cat of that. Now you changed the value of the console log level. Try to insert the module. So now you see the message is not promoted to the console because the current console log level is 6 and our print case log level is also 6. That's why the message is not promoted to the current console. If you want to see that message, you have to run dmessage. Let's run dmessage. So you see the message here. Now I hope you get the idea of why kernel log levels are used with printk. The kernel log levels are compared with the current console log level, and based on that, kernel takes the decision whether to submit directly into the current console or not. Let's move forward. But in our code, we didn't use printk API. We actually used wrappers. Instead of writing the log level and the message, you can use a wrapper function. For example, instead of using printk kern info message, you can use its wrapper macro, that is pr_info. This is nothing but a macro which wraps this function. That's why for kern emerge, you can use pr_emerge. For kern alert, you can use pr_alert, and so on. So while writing your kernel module, if you want to report any error, then you can use pr_error. And if you want to send some general information, then you can just use pr_info. And if you want to send any warning, then you can use pr_warning. And if there is any critical problem, then you can use pr_crit or pr_alert. I hope you remember this. And these wrappers are defined in Linux printk.h. In the next lecture, let's get started with writing a simple character driver. I'll see you in the next lecture. Hey, welcome back to the lecture. From this lecture onwards, let's explore about device drivers. First of all, what is a device driver? Device driver is a piece of code that configures and manages a device. The device driver code knows how to configure the device, sending data to the device, and it knows how to process requests which originate from the device. When the device driver code is loaded into the operating system, such as Linux, it exposes interfaces to the user space so that the user application can communicate with the device. So without the device driver, the OS or the application will not have a clear picture of how to deal with the device. Basically, device driver is a code which knows how to handle a particular device. It gives a right interfaces for the user space to access that device, and device driver code also abstracts various hardware details from the user space applications. The user space applications can just use traditional write, open, read system calls to talk to the device. But those system calls are carefully handled by the driver code to touch various registers of the device. The kernel's job here is to connect the system calls to the driver's system call implementation methods. Let's say there is a device XYZ, and when you load a driver of that device, then the device driver exposes